All right, let's. I changed that. There we go. Let's open it up. There's our template. Just gonna try dark mode. See how that goes. Oh, wrong one. Not that one. All right, let's see. We'll just start here. Okay. So, we'll start off with our structure and see. Okay. So, just grab this as an example. I feel like there's a type define that you can do. Oh. See, struct type def that people like to do. Yeah, I think people typically don't want to have to type struct all over the place. C sort of did a poor job of defining how exactly that should work. So, instead of just saying struct, we can say type def. And then you put the, I always would forget this, at the end. It'd help if I can spell type def. There we go. Oh, I did this backwards. I should read. There we go. Oh. So if we want a pointer, malloc size of my structure. And malloc is, I should clean up that in the 64-bit. Okay. Doesn't do anything. Perfect. All right, so we can malloc that size, and then we can say m arrow. My letter is equal to a. And I'm going to use, let's see, standard int. Because I don't like using regular ints. So this is a u int 32. All right. So if we go ahead and say dump the name of our structure, and the function we want to do is main. All right, so let's look at this. So we got a malloc here. Malloc is in the PLT. We're taking that return address and we're moving it to RBP -8. And then we're loading that back into RAX. And then, so let's see, 61 is in RAX +4. So this is taking up 4 bytes. And then this is takes up 1 byte, but unless you declare another character, it's going to have a different offset. And then we can see that it also takes and moves. We reload the variable into RAX, and then we move feed beef into it. So I think, if you are trying to learn this, you typically want to put in some constants that you can figure out what they do in sort of a trivial example, and that will help you to understand how they're going to work as it gets more complicated. So, for example, I was saying these take up a certain amount of width. So it depends on the alignment. So this is doing 4-byte alignment, I'm pretty sure. So for example, if we declare another char, another letter. So this, I think, is going to take up 3 extra bytes, take up 4 bytes total. So that means this access into RAX is going to shift by another 4. So you got to understand where they're going to be laid out if you're going to do it in a efficient manner. Make and dump. So now we can see that feed beef is at offset 4. And the letter A, which is hex 61, is at offset 8. So we got 4, 8, and then if I were to access this, another letter is equal to the letter B. That should go at the very beginning. So letter B is 62, so that's at the very beginning, and then this took up, I gotta grab the right offset. So this one is at offset 8, and this one is at offset 4. We can also see exactly how big it thinks this is, so we can see here EDI has 0xc, so it takes up 12 whole bytes. So if I just move this up here, and so now I have my two characters, they'll actually be compact when it accesses them. Let me grab the window here. Okay. So now instead of it taking 12, it takes 8. So typically the C standard says that things are going to get aligned on a 4-byte boundary. C align. Trying to see where they... Yeah, if you want to understand, right, so data structure alignment, and this goes a lot back to how fast it is to load certain things when they are aligned versus when they are not aligned. So typically there are different loads for those. As far as I understand, I think the impact is a little less now than it used to be. It used to be quite a big hit when you had bad alignment, but that's kind of how it works. So, you know, if you're trying to learn this, right, the more that you sort of get into this, you can sort of understand it better. So I'm gonna move this. Let me scroll appropriately. All right, so let's move this back. So it's gonna try and do 4-byte boundaries for all of these, and you can see that, right, the single character followed by something that took up more bytes is going to really show that to you. You know, we could have used a U64, and then let's see what the alignment is on that. All right, so yeah, my letter is at RAX, and then this is going at byte 8, right? So this structure, it wants to align on an 8-byte boundary. So it's adding 8 to that, and then yeah, that's an 8-byte boundary. And then this is at offset 16 because this is going to take up 8 bytes. Right? 8 times 8 is 64. So this takes up 8 bytes, so it's going to have to go to 10 and hex, which is 16 base 10. And we can look at a uint 16. We can add that. So let's do my letter, and then we'll do my short. So we should get A, and then our short. A is there. So this is going to go to a 2-byte boundary. So it'll start at offset 2. Right, and if this was on an even boundary, so even if I put this, we can see, let's see, our allocation is hex 18. I think the minimum we would get is if we actually moved this up. Oh, sorry, I don't move it there. If we moved our 64 at the beginning, like if you reverse size orient it, you will probably get as good most times as you can get. So you typically would want to put the 64 and the 16 unless you had some reason for doing it You know, you can use things like unions to say that something could be multiple types. So that's something that you could do, but this allocation should be pretty small, right? So our allocation here, the parameter going to malloc is 10 hex. So we've got 16 whole bytes. We got 8. And here we got 2, 9, 10, 11, 12. So we got 12 out of the 16 bytes. So we could either make this an array. I think I can do it that way. Oh. I think I gotta say how big it is, so I could do 3 characters there. And then another letter, bracket 0 equals a B. And I could do 2 is a C. And you can see here, it's going to do the math sort of implicitly. So it's going to do the offset calculation plus the array calculation all at once. Unless you've got a loop that's going through, and then it wouldn't know what that offset is. If it can calculate it beforehand, it will go ahead and do that calculation. And let's see, let's do unions, because I think that's fun. Let me find a good example. Yeah, so I think I can just say union. And let's use a uint 8 underscore t. My short array of size 2. Oh, do I have to give it a name? I'm trying to wonder. So C is a little different in this. Oh, I think I have to say this. There we go. So now to access it, you have to decide how you want to do it. Dot shorty. Oh, and of course I changed that. So it actually should access the same. So shorty is 255. Again, it just does the calculation. But you could use s array bracket 1 to set one of them. So this will set that byte to 255. Let's see, does that fit in a byte? 2 to the 8. Yeah, 256. So when we look at our offset, so before our offset was 8, so then it should be 9, right? Oh, and I did that in hex, so I can't do hex 255, hex FF. If I'm going to do a short, I was thinking decimal. There we go. That should be right. Yep, FF. Right, and typically you might use it if you're not using sort of these built-in types, or you want to use a larger one. So we could actually use something much larger. Uint 64T long E. And now that's going to take up more space, right? So my letter, what offset was my letter? My letter got A, right? And it came after it. So my letter was 60, yeah, 61, but it was at offset 10, or A, offset A. So now when it goes to make this structure, it's going to pick whatever thing is the biggest in order to make it. So I happen to pick a U64T, but you could do an array, you know, whatever you wanted in order to make that bigger. So now we can see that our A has gotten pushed back, right? Because A comes after it, and the way that C does the structure is it bases on the order, does this alignment. Unless you tell it to pack it, it doesn't do that. And you typically don't want to pack unless, you know, the reason that they have this is so that the structures, when you pass them between different functions and possibly even different operating systems, like it would be the same. Typically, if you're going over the network or whatever, you'd have to have some sort of serializer to put it on the wire, unless you wanted to directly send the bits. Which is why a lot of times, you know, if you look at Microsoft structures, when they define, for example, headers for their PE files, they will use, they'll put in reserved bits and or reserved words, D words, so that way people know that there is additional stuff. So let's look at some Microsoft structures. Let's see if it has it here. Yeah, so they will define, first of all, they'll define things in hex, so that way people know what it is. They'll define exactly what the size is. Right, so here we have an offset, so the offset into, so this is a cough header file. The one I wanted, I think, was a PE file, so let's see. Yeah. Not sure if this has the... I know there's a... well, they have the DOS stub. Alright. So very, very explicitly, right, it has listed, here are the offsets, right, and then these, I think, are, well, there is a size that says what it is, but you will see in here, let's see. Well, this isn't going as detailed as I was thinking it was. No. these are that's what I was looking for. Yeah, so you can see here, right? Microsoft goes ahead and they use things like word and long, which have very specific meanings. I believe a word. Trying to remember if a word is 32 bits. Yeah, their Win API defines these. Oh, so word must be 16. Oh, I should have just. Yeah, word is 16. D word, well, yeah, DB, D word. And then long should be. Oh, I just destroyed. What the heck? Well, completely shut off Chrome. And now everything is going opening up. Okay. Long. And of course they define a bunch of different longs. That's U for unsigned. P, oh good, a pointer. Pointer to an unsigned long. H, JKL, 32 bits, all right. So this is 32 bits, this is, all right, so they have quite a few, right? So 16 bits times 10, that's 160 bits that they have reserved in there. So, you know, if you find that there is, you know, some padding that you are concerned about, you know, for example, this is going to make sure it's on at least a 4-byte boundary for this portion by adding this either as that, or again, you could define a union of that and then the array of bytes in the total size that you want. Right, so those are a couple different ways you can do that. So, I'm not sure if you guys had any questions, but I thought at least we could look at it, and then this sort of provides the basis for when you start getting into C++. And we can talk about that. Let's see, object. I'll have to remember my C++. Yeah, oh, vtables, my favorite. Right, so the way that C++ manages your this keyword is it uses a pointer to a vtable, so a virtual table which has functions. This is a pointer to an array of pointers, and those pointers will point at functions. And so they do this because then and then each time you extend a class, right, it sort of embeds in it the other class. So the new class that you create is going to have the fields defined in the superclass, as well as a vtable pointer, and that vtable pointer is going to point to that superclass's methods. And because it points to those methods, that way when you downcast an object, it will be able to call the appropriate methods for the parent as opposed to calling the overridden ones for the child class. And so it enables you to downcast very easily. Upcast means you're going to have to like take your structure that's here in memory and you're going to have to subtract from it to get to that other class and hope that it is right. So that's a whole thing. So we will probably take several streams in order to look at it, because I'm going to have to remember exactly how to do C++ and the virtual functions that it has. So, all right. Well, I think that is all we got for today. So I hope.
Hardwired.
It's hardwired into your brain.
Oh gosh. For today, I have to log into. Okay. All right. Well, I hope it was a good Friday, and I'll see you next week. Thanks, guys. Talk to you later.